We're about to be regaled by three quintessential Midwesterners here. Mr. Nick Johnson is from Boonville, Indiana, a graduate of Boonville High School. Mr. Jordan Foose is a graduate of Gibson Southern High School in Gibson County, Indiana. And finally, Mr. Travis Stitch is from Lawrenceville, Illinois, a graduate of Lawrenceville High School. And these gentlemen are going to be telling you about the Baja SAE steering and suspension design for next year's Baja SAE off-road vehicle. Gentlemen.
All right, good afternoon, everyone, and welcome to the USI Baja SAE suspension and steering design presentation. As Dr. Kissel said, my name is Jordan Foose. To my left is Nick Johnson, and on my right is Travis Stitch. To start off, we'll give you an overview of the things we're going to cover today. First, we'll introduce what the Baja SAE competition is. From there, we'll give you the definition of the suspension and steering system. Next, we'll talk about the requirements that both Baja has for us and that we put in place that constrained our designs. From there, we'll talk about the front and rear suspension design, followed by the steering design, and then we'll have our design conclusions, and at the end, we'll open it up for any questions you guys have. So first of all, SAE stands for Society of Automotive Engineers. And the Baja SAE is an intercollegiate engineering design competitions where students must function as a team to design, test, and build a vehicle within the limits but set by the competition. During the competition, there's 4 dynamic events. The first being an acceleration run. This is similar to a drag race where cars will compete against each other and race to the finish line as quickly as possible. Next, there's a hill climb. Following is a maneuverability event. This is usually a course set up in a wooded area. It's primarily focused on the steering of the vehicle. And then the following is the suspension. This is a course outline that has lots of boulders, rocks, logs, and foreign obstacles that the vehicle has to go over. And the following day, on the very last day, there's a 4-hour endurance race that the vehicle has to compete in. This endurance race encompasses all 4 of these dynamic events. And as you can see from the video, there's pretty rugged terrain, those concrete boulders and the logs and all the jumps. Our suspension and steering system has to be designed well to withstand these obstacles. Here we have a subsystem breakdown of the overall vehicle. You can see there's the steering, the suspension, the drivetrain, the electronics, and the frame, and we focused on the 2 highlighted in yellow. So the objective of this project was to design a complete front, rear, and steering system that would optimize the newly designed frame, which you heard earlier today from the other senior design group. Now Travis will give you the goals of the suspension and steering system.
Thanks, Jordan. There are 6 goals when designing a suspension and steering system. The first goal is you must keep the tires in contact with the racing surface. The second goal is to maintain the desired ground clearance. The third is to support the vehicle weight. The fourth is to reduce the effects of external forces. The fifth is to maintain the proper wheel alignment. And the sixth is to control the direction of the wheels of travel. The suspension systems are located at both the front of the frame and the rear of the frame, with the steering system also located at the front. Each wheel will have an independent suspension system, which will allow the vehicle to navigate over rugged terrain. This is the present USI vehicle. This is what motivated our design. We found several issues that they had in the past with this car. The first was the weight of this vehicle. It is much heavier than several other vehicles of the competition. Reducing the weight of the suspension system will help reduce the overall weight of the vehicle. The second issue was low ground clearance compared to other vehicles. It is currently approximately 11 inches, and we plan on increasing that to about 14 inches. Then focusing in on the front suspension, we found 2 main design flaws with it. The first is the team used a double wishbone type 2 suspension. The issue with this is it requires a large vertical space, which required the frame to be taller than what it should be, and this restricted the driver's view of the track and also led to a safety concern. The second issue is with the steering system, the turning radius was very large and the vehicle was very difficult to maneuver around obstacles. Moving into the rear, the problem with the rear suspension is it wasn't designed. It was thrown together at the last minute, kind of as an afterthought, and it's also a double wishbone type 2 suspension, which isn't normally found in rear suspensions, it's more common on front suspensions. It is very stiff and provides a really rough ride for the driver. This is the suspension system broken down into the front suspension component and the rear suspension component. In the front suspension, you have the upper control arm, the lower control arm, the knuckle, and the shock absorber. In the rear suspension, you have the trailing arms, the camber arms, the shock absorber, the hub assembly, and the drive axle. Like Jordan said, the components in yellow is where our design was focused. And we wanted to give you guys a visual representation of where these parts were located within a suspension system. And we've highlighted those individually in red, starting out with the upper control arm, the lower control arm, the steering knuckle, and the shock absorber. And then in the rear suspension, we have the trailing arm, followed by the camber arms, and lastly, the hub assembly.
So when we start talking about a steering system, we have to define what a steering system is. And a steering system is what you use to navigate a car along a selected path. And inside of the steering system, you've got a few different parts. You've got your steering wheel, your steering shaft, the rack and pinion, the tie rods, and the knuckle. And what we designed were the tie rods and the knuckle. And to put some pictures with the words, we've got your tie rods, the rack and pinion, and the steering knuckle. So our requirements for this design, one, the very first requirement that we have was set forth by Baja SAE, and is that the vehicle can't be wider than 64 inches. The second requirement we put forth, and this requirement was put in place so that we could navigate over the top of bigger obstacles, and that's to have a ground clearance of 14 inches or more. Our third requirement, the vehicle needs to have a smaller turning radius. This will help us in being able to navigate the course more efficiently, and our radius needs to be either 69 inches or less. And for our last requirement, the suspension system and steering systems combined must weigh 50% less than the current vehicle.
Before we get into the actual design, there are three key parameters, three key alignment parameters that must be kept in mind in both the front suspension and the rear suspension. As you can see, we have camber, caster, and toe. Camber, if you're looking at the front of the wheel, if the top of the wheel is angled in towards the vehicle, there is said to be a negative camber. What negative camber allows is the vehicle to apply an even loading over bumps and during cornering. Looking at caster, if you look from the vehicle out towards the wheel, you can see the caster, and if the steering axis is tilted towards the rear of the vehicle, it is said to have positive caster. An example of positive caster is a shopping cart at Walmart. What positive caster allows is the front wheels to return to the straight position after making a turn. However, if you have too much positive caster, it makes the vehicle difficult to turn. Finally, we have toe. This is a top-down view looking at the wheels. If the tires are angled in towards each other, there's positive toe, also known as a toe-in condition. This will allow the vehicle to maintain straight line stability at the sacrifice of turning. Now we'll move into this front suspension design. And there were three design concepts when we started this design that we were looking at. First, we have the McPherson strut. It's commonly found on front-wheel drive production vehicles. The reason for this is it's a simple design, easily fabricated. However, it doesn't allow you to easily control the alignment parameters that I just discussed. For this reason, we have eliminated this. The second type of suspension is the double wishbone type 2. This is the suspension that is presently on the current vehicle. Like I mentioned, the issue with this is it has a large vertical area required, and we wanted to eliminate this to give the driver better visibility. So we've eliminated this. The double wishbone type 1 is the design that we will be using for our suspension. Here you can see that the shock absorber is mounted to the lower control arm instead of the upper control arm, which again allows us to reduce that vertical space needed. The control arms, both the upper and lower control arms, were made of 4130 chromoly steel tubing. The reason for this is it's a material that's already been approved by Baja SAE. If we were to use another material, we would have to go through and prove the strength is equal to or greater than that of 4130 chromoly steel. Also, we selected the 1-inch outer diameter by 0.12-inch thick wall tubing because we already had this from the frame design, and so we wanted to utilize this as well. We'll be using heim joints at the frame interface, and this will allow us to control the camber as well as other adjustments. And we will use tie rod ends at the knuckle. The upper control arm is 13.41 inches long, and the lower control arm is 16.23 inches long. The reason for the unequal lengths is to maintain a favorable camber during turning and over obstacles. This is the final SolidWorks assembly, and here you can see the control arms mounted to the frame as well as the knuckle, and you can also see the shock absorber mounted to the lower control arm and to the frame. We had to work with the frame team to ensure that their design would work with our design, so we were going back and forth several times just to get the right setup. This design allowed us to have the 14 inches of ground clearance that we desired while staying within the 64-inch width set forth by Baja SAE. This is just a comparison of the current vehicle to the new vehicle. The current vehicle did utilize the equal length control arms, and this was the largest change where we switched to the unequal length control arms. We also went through several iterations on camber, caster, and toe to kind of find the best fit for all the competition, the different events. We ended up changing from 0 degrees of camber to -2 degrees of camber, increased the caster from 6 degrees to +8 degrees. The toe will now be adjustable depending on the event of the car we're running in. And we increased the shock absorber angle from 25 degrees to 34 degrees to increase the range of vertical travel of the suspension.
So now we'll talk a little bit about the rear suspension. Again, we had three different concepts that we wanted to take a good look at. We had the double wishbone type 1, which Travis utilized in the front suspension design. This would not work in the rear suspension. We have to interface around the drive axle, and the drive axle can't really go through a shock. So we did away with that. The double wishbone type 2 is what's currently on the car. And like we said before, it called for reinforcing the back end of the frame. And since the frame has already been built, for the most part, we didn't want to go back in and reinforce and redesign. So again, we did away with the double wishbone type 2. And we did a trailing arm design. Now our trailing arm will be made out of 4130 chromoly steel for the same reasons that we picked 4130 for the front suspension. The length of the trailing arm from the mounting point to the center of the hub will be 23 inches to get our geometry right. And then the camber arms work a lot like the way the control arms work. The unequal links give us good camber variation, and it gives us the right geometry. Now here you can see the whole assembly of the rear suspension. Using all of those links gave us the 14 inches of ground clearance and much less than 64 inches wide. And in this table, you can see that there's really not a lot of difference as far as the alignment parameters. What is different about this new design is that everything's adjustable. So if for some reason the camber would get out of spec, somebody could go in there and readjust it and make it right. The biggest change, other than the configuration, is the shock angle. Shock angle is much higher. This will allow for a lot more vertical travel with a lot less linear travel in the shock. For the shock absorbers, we picked Fox Float 3 Evol Air shocks. The biggest advantage about these shocks were that the shocks only weigh 3 pounds apiece, which compared to the shocks that are on the present vehicle, which are about 25 pounds apiece, it helped us meet our weight requirement really easy. And as an added bonus, these air shocks are also adjustable. So we can adjust the ride height of the suspension and even the damping coefficients of the shocks themselves by adding and removing air from different chambers in the shock.
So now we'll move into the steering design. To start off, we'll go over a picture with the components in there. Again, like I said, we have the steering knuckle for both the left and right. Mounted, fabricated onto the steering knuckle is the steering arm. Then there's the tie rods, and then the steering system, which in our case will be a rack and pinion. And then you also have the steering shaft coming off the steering wheel that connects to the rack and pinion. So for our design of the steering system, we primarily based it upon the Ackerman condition. If you look at this image at the bottom, it shows this vehicle making a right-hand turn. And if you look closely at the red lines here, those are the tracks from the 2 front tires. And as this vehicle travels around the turn, the 2 front tires are actually traveling around 2 different radiuses. You can see the outside wheel is traveling around R1 and the inside is R2. So to achieve this 2 different turning radii, we have to implement this Ackerman geometry. The Ackerman geometry is a trapezoidal geometry as shown on the right, where the steering arms come off at an angle. The steering arm has 2 main components that it's designed around, which is the steering arm length, D, shown on the left-hand picture, and the steering arm angle, beta, also shown on the left hand. This next image is an image of the current setup. It's a little congested because it's a picture with, it has control arms and the tie rods and the hub and everything on the vehicle. But we measured the steering arm to be 2.375 inches and the steering arm angle to be 12.15 degrees. This did not give us the true Ackerman condition, and the 2 front tires did not travel around the same radius. So to achieve this, we had to increase the steering arm length and increase the steering arm angle to those numbers shown there, which allowed us to achieve the true Ackerman condition. This table here kind of sums up everything, the design for the front steering. As you can see, we did meet our requirement for the turning radius, and actually that came below our minimum requirement of 69 inches. We had 64 inches. The steering arm angle and length both had to increase to meet the true Ackerman. The rack and pinions, we're going to use the current one that's on the car. There was no issues with it, so we'll be using it again. And then the tie rods increased by roughly 1.5 inches due to the suspension geometry change. So this table here kind of sums up all of the things, how we met our requirements. The width for the front increased 1 inch, which still kept us within the 64 minimum requirement or maximum requirement. Like I said, the turning radius was decreased quite a bit from what the current design was. We increased our ground clearance by almost 3 inches and reduced the weight by almost 100 pounds. And like Nick said, this was primarily due to our shock change. This table here is a list of all the items in our project. Most of these items have not been purchased yet, but we had a grand total of $4,351.21 to to complete and fabricate our systems. There's lots of people we have to thank for us getting this completed, mainly the faculty and staff here at USI, but more specifically in the engineering department. Without their help, not only this semester, but the past 4 years, we wouldn't be where we are. And we'd also like to give thanks to our family and friends for helping us along, too. At this time, we'll open it up for any questions.
Questions?
Nice job. You mentioned some of the, like the toe was adjustable. I was just wondering kind of what that would entail. You're talking about like between events, how does that work?
Yeah, basically, if you're during a suspension event or the maneuverability event or even endurance race, changing, there are nuts on the tie rod ends, and you can either widen that or shorten that, and they'll give you your toe in condition or a toe out condition, whichever better suits the event.
The tie rod seems to be a common point of failure in the Baja competition. And I didn't see a whole lot about construction materials. Is there any advice you could give to the future builders, presumably in the fall, about how to construct those tie rods or protect the tie rods from impact in the race?
Yeah. Well, we planned on using the secondary members, which is the 35 thousandths thickness. I know at the competition this year, they said that they did have a failure, but it was within the tie rod, it wasn't within the member. So I think sticking with the secondary member will be sufficient for that.
Other questions?
You guys mentioned a couple numbers for optimum caster and camber for the car, for the front and rear end. How did you arrive at those numbers? What did you take into account to come up with that?
That was definitely a trade-off between the suspension travel, what's optimal for the steering, and then what was optimal for the suspension. There were several times Jordan and I were arguing. You know, he wanted a positive camber, and I wanted a negative camber because they affected us differently. But in the end, we were able to compromise and reach the best solution, and those are the numbers shown.
Yeah, it was a good job on the presentation, but my question was on the 3-inch lift you got, what did that do to stability of the vehicle on turns and stuff? Did that make it harder to control the turning?
Clearly, that will increase the roll of the body, but how we mitigated this was, again, with the unequal control arm lengths. That does offset the increased body roll, so that's how we were able to, mitigate that risk.
So you guys redesigned the rear suspension, and I think that's really good. I think we're seeing that in a lot of the competitions. Can you speak to the robustness of it? How would it handle against the suspension that we have now?
So one of the big things about the rear suspension right now is it is really robust. The control arm configuration, like the A arm, it's really robust. But we did run a little bit of FEA on the different parts. Now, with a force of 300 pounds in the rear, where that shock is coming down at, we still had a factor safety of 2.3, which, so, I mean, I don't see any reason that it wouldn't hold up to it. Probably want to, go ahead.
I was going to say 300 pounds is basically just the driver and
that's on one side.
Oh, I
You've
see.
got two, so that's 600 pounds. I mean, and then you've got another 300 pounds on the front, so you're looking at 1,200 pounds on the vehicle,
Nice.
and it's holding up, so.
Good, thanks. I've got a question on your design of the trailing arms. I noticed they came out at an angle and you've got the short, straight piece to tie in perpendicular to the frame. Why not just go in and actually put your mount on the frame at an angle? I feel like you have a lot of torque force, the way that's mounted currently with your mount being in a straight line, but your trailing arm coming off at an angle. I feel like any kind of a twisting motion is gonna put a lot of strain on those mounts.
You're talking at the hub or at the frame?
No, at the frame, where the front of the trailing arm.
So you're talking right here?
Yeah.
I'm kind of lost of where you're
Okay,
getting
you've
at.
got, the lower part of the frame runs from right to left, it's perpendicular to the direction of travel of the car, right?
Sure.
So your mount right now is coming straight out in line with the travel of the car,
Yeah.
but your trailing arm comes in at an angle.
Yeah.
So any kind of up and down force, you're actually trying to twist that mount where it attaches to the
Okay.
frame.
Yeah.
Could you potentially move that mount to fall in line with the angle of the trailing
Well,
arm?
what actually, in that design, we've got a Heim joint at the front of that trailing arm, and that Heim joint will allow for that to rotate freely, and it's actually got up to 22 degrees of travel before it ever starts even getting in a bind.
Okay,
So,
I missed the high part of that, I thought it was a fixed angle.
yeah.
Hello, well done. I have a couple of questions. The first one is, what part of the project did you enjoy the most? And the second is, if you were to start over again, what would you different? What would you change?
Better flow operation.
I don't know that I'd call it fun. I mean, it was fun, just being able to work with each other and get something done, and come up with something that looks good and that's gonna work and that will work. That was awesome to see. Probably the one thing that I know we would all do different would be to work more closely with the frame design team to get a couple of our changes to make it our job a little bit easier and to not make as many modifications to the frame.
Good, thank you.
All right, any other questions? Let's give them a hand.